is it's about information freshness. It's about wireless IoT network. So many talk about from the perspective of multi-user scheduling. So I think those who is familiar with information theory society, they may notice there is each year in ISIT, there are maybe several papers on these topics. Also, this is a cross domain or society, because there are also other people in networking society also very active in this topic. For example, in Infocom. When you see Infocom, the call for paper list of topic, the first one is age of information. And I just saw Parastu's background very interesting, ISIT 2021. It's good to know that you will be in Melbourne, Sydney, Melbourne, Australia. And I hope we can meet there. I hope at that stage, everything is back to normal. So as Van Chen said, I'm now in Chinese Uni of Hong Kong. I lead in the wireless IoT System Group. So today's talk, there is a lot of work joined with the Center of IoT and Telecommunication in Sydney Uni, where I work with Yonghui, Branca, and the student there. So here's a quick outline for today's talk. You can treat this one as a brief tutorial on age of information. I want to keep it general, high level, and so you can get some take-away message after my talk. So the first is we want to answer a question why we need fresh data. The second one is age of information. So it's a new metric for information freshness. And then we'll talk about two ways of optimizing information freshness. One is from scheduling perspective, one is from random access perspective. Finally, I'll talk about some prototype of experimental study of this AI-oriented design that I have been done here. So maybe I'm new here, so let me briefly to introduce you what our group are doing here. So for those who may be familiar with me, knowing that basically I'm doing theoretical communication, wireless communication research when I was in Sydney, but now I gradually moved to experimental kind of research. So we do basically both theoretical and experimental research. So we mainly have three research areas. The first one is wireless monitoring. Basically, we use IoT technology to monitor wireless IoT technology to monitor a lot of things. For example, today's talk about information freshness is actually part of this area. The second one is wireless control. It's also an area that I was involved when I was a postdoc in Sydney Uni, and then I also keep working on that here. So we basically want to, if you see today's factory, most of the communication there is wide communication. Though wireless is part of everyone's life, but in factory, in the industrial world or in factory world, it's not that case. So because wireless has not been designed for serving machines, because it has been designed for serving people. So we basically want to design very reliable. In a wireless communication society, it's called UILC. And when you go to the industrial automation area, people say it's wireless time-sensitive network. It's actually the same thing. The third one is we are doing wireless sensing, means we use wireless signal to sense. The main application is for healthcare. So I call it. Let me enlarge it. I call it wireless IoT System Group because we really build systems. So, for example, we have a lot of USRPs. We do design this AI-oriented protocol design, and then we implement on this and test it in our office environment. And also another project we are doing is, this is Raspberry Pi plus a LoRa module. So what we want to do is we want to improve the default LoRa protocol by using more advanced technology. But we finally, the finals, normally previously when we published paper, we stop at simulation, but now we want to push forward, we want to implement our algorithm and test it in the real environment. In terms of this wireless control part, we both work on this soft-defined radio solution, also commercial Wi-Fi solution. So because today there are already some commercial Wi-Fi system used in the factories. So what we want to do is, because the commercial Wi-Fi use CSMA, then the delay performance is not good. So we basically try to change CSMA to TDMA. But when we're doing this, we need to have a lot of dirty work. Actually, we need to go into the Linux kernel and try to decode and debug a lot of things. And also, actually, recently we are focusing on is actually in industrial network, synchronization is very important point. But in our most of the research in wireless communication, we assume perfect synchronization a lot of times. So, but Wi-Fi, if you only change the, software level, the kernel level, it still use the computer clock to do synchronization, and that is not enough. So we are trying to do is we connect this one with another FPGA, very cheap FPGA board, and this FPGA board is for synchronization. And we look forward that this kind of things will be much better than if you only use software solution only. And another kind of things is we do soft-defined radio, but I think if someone knows soft-defined radio, you may say, oh, people use USRP and use PC to do signal processing. This is soft-defined radio. But recently, there are new soft-defined radio. Basically, it's ARM plus FPGA. So basically, we do signal processing. A lot of things need to put to FPGA in order to get very, very good latency or reliability performance. And a lot of other things, for example, MAC protocol and higher layers we put on ARM. And there are recently this SoC chip, system on chip chips and this development board from Dalins. So we basically have based on some open source project, we already built use this kind of thing to build a Wi-Fi AP. It can be communicate with your phone. So we implement everything on the physical layer and also the MAC layer and application layers. But this we want to move forward is we want to change a lot of things in the physical layer or even in the MAC layer to make the system really ultra reliable. So ultra low latency. So what we want to answer is, for example, for point-to-point communication, what will be the minimum latency, including everything, decoding, coding, and demodulation. We want to push it to the limit and see what will be the answer. But I think another problem in the UILC domain is, although you do very well in your system level, but in the air there could be interference. So we have been trying to think about to solve this problem. Although 5G can solve it because 5G has dedicated spectrum, but currently most of the industrial applications, they use Wi-Fi spectrum because it's free. Why not use 5G? Whether we will use 5G, it's hard to say because it depends on, it's really need a very, very good model to motivate the factory to use 5G. Because, for example, I need to rely some people from external, from mobile operator to operate my network. Although they are private 5G, but what will be the spectrum? That is still an issue. So we have been thinking about to use light. I think many of you know Li-Fi. We have been thinking to integrate our system with Li-Fi, and because light is actually a short range and and more secure. It's hard to jam. It's hard to eavesdrop. But there are also other problems of Wi-Fi because you need to do the very good source and destination because it's LOS communication. So when it's have a probability, when you want to have mobility, how to make sure the performance is good. So this is what we are trying to solve here. And in terms of the third part is this about wireless sensing. We mainly use it for healthcare. So we have been working two parts. One part is to use Wi-Fi signal to detect the vital signal, like such as the breathing and heartbeat of human being. And we have already demoed that. It's not hard. There are a lot of work already working in that area. But what I'm doing, because I'm from physical layer, this kind of work is originally from computer science people doing that. So what I'm doing is we are trying to use some very advanced physical layer technology into the system and see how we can improve the system further compared to computer science people doing. We also use radar because radar previously is very expensive, but recently radar is less expensive. And also how you integrate radar and the communication part, I think is a very recent hot topic in our society. So this is basically what we are doing here. There actually, to be honest, there are a lot of dirty work when you try to do this kind of things. But I found them very interesting. So if you are interested in doing that kind of work, because we have go through all the tricks. If you need any help in this kind of thing, try to contact me. We will let you know what we have suffered from and our solutions. So now our team has 5 research students and these two students are actually Yonghui students from Sydney, but they also work closely with me. And we also have 2 RA working on this dirty works. Okay, so this is basically what we are doing here. So let's go back to the talk today. So we are talking about information freshness in IoT. Actually, this IoT concept is not that new. It's coined in more than 20 years ago, and we already talk about IoT a lot and say IoT is here, IoT is there. But some people may say, oh, IoT comes too many times, whether it's for car, when it's for car. So both is coming too many times. So, but what I want to say is IoT is actually really coming. This is a hypercycle IoT curve from Gartner. I think many of you know this. This is a company that predict the trends of a lot of technologies. And you see there are different, there are different points on the curve, and different color denote different, whether it will come less than 2 years, 2 to 5 years, or 5 to 10 years, or more than 10 years. So it's good to see that many of them already within this one is within 2 years, is IoT integration, and several of them are in this light blue color, meaning it will come within 2 to 5 years, and this dark blue one is 5 to 10 years are there. So for example, digital twin will come 2 to 5 years. There another one is to come to 5 to 10 years. We also work in this area is digital twin for people. We basically want to build a virtual model for people's health. And then we collect the heart rate and the sleep and a lot of other data, and then we reconstruct the model in the computer, and then we can predict the health of the people, especially for these old people that live alone. We need to use technology to take care of their health, especially in this area of pandemic. So a good point to see that we have already talked about these autonomous vehicles. We say it will coming, but according to Gartner, it will not be coming within 10 years. So there are lots of other issues except this technology part. I think you may already read the report on that. For example, there may be some issues For example, when a car need to make a decision, hit people, then it will the car itself will be safe, and the people within the car will be safe. But if it try to avoid the people ahead, then the people inside maybe go to death. So how to make the decision? So that is a not technical issue, but this need to be addressed before this technology can be used. Okay, and according to an MIT technology review, here they said there's 3 classes of IoT devices, but the first one is consumer IoT, is mainly used in our daily life. For example, smartphones, a lot of other things. Another one is business IoT. Business IoT includes a lot of vertical market, for example, transportation, fleet management. For example, you are running a truck company, and then you want to use this IoT technology to track where is your truck, and a lot of other things. This is business IoT. And what we are focused is on this industrial IoT. So it includes manufacturing and these smart cities, and also healthcare, utility, a lot of other things. So this IoT deployment will transmit data through gateway and send the information to the cloud for remote access or analysis. This is basically industrial IoT. Let's see a few examples of industrial IoT. So we have smart transportation. We say in the future, car will be connected and talk to each other, and say report the status. For example, it may report, oh, I need to this car, I will slow down, and then all the car will be informed after that. I will change lane, and this car may be informed. So this is smart transportation. Smart parking, a very hot, important topic. Part of smart city is we basically get the parking slot connected to internet. And then before people arriving parking a building, the parking area, he or she knows how many parking spaces are available there, where I should go. This is another application. We mentioned this smart healthcare. We basically monitor the everyday vital signal of people, and then send this data to the cloud. And then the professions can access this data and provide professional advice. So also this smart factory, in this industry 4.0, more and more automation will be used. For example, robotic arm, this kind of production lines. We basically want to monitor the status, even the health status of robotic arm. We want to do basically predictive analysis or predictive maintenance. These people sitting in the office want to see the data of the production line. So if they see any potential problem, they can try to do something before the production line really stuck, and it will be cause a lot of loss, or some problem may cause maybe people get injured. So we also need to collect a lot of information and then send to a control center. So in the previous application, we all see that this involves some remote monitoring application. So by remote monitoring, I'm saying that there are various sensors monitor certain physical process, send its sample status to the monitor, sorry, typo, send the monitor data to a remote monitor. We normally call this one a status update system. So for example, in this one, we may send the status of the robotic arm to the office. The technician may sit in office and then monitor the health condition of the robotics arm. This one, we send the data, the status of people to professions. This one, we send the status of the parking slot to people that subscribe to the service. So you will see that in this kind of service, information is usually has highest value or valuable when it is fresh. For example, for the smart parking situation, if you send some status outdated, you will get people annoyed. I go there, I found, you told me there is a parking slot. I go there and there is no parking slot. So then I feel unhappy about that, right? So we need to try to ensure that the information or the data here are very fresh. Then a natural question come up is, how are you going to quantify the information freshness? So this is the question we want to answer in the next part. Is basically the answer is the people propose AOI, age of information. It's like age of people. How old are you? It's how old this age, the packet. So there are already some existing common used performance metrics in this communication network. For example, throughput, especially determine how fast you send the data and what is your error probability. And also packet delay. An extension of packet delay is packet inter-deliver time. Is from last time I receive a packet and then till the next time, till the current time I receive a packet, what is the duration for that? And this is the existing one. But I want to say that this kind of measures may not be good for information freshness. For example, if we want to do delay minimization, we basically do not want to send a lot of, I use a buffer to model the channel. We do not want to send, or the network, we do not want to send a lot of data to the network to cause a lot of things to queue here before it serves. So in this case, to minimize delay, we should avoid sending the status update too frequently. But this may be not good because even you send this one, for example, this one to the network and instantaneously serve, but this one may be generated several times, long times ago. Then, although I receive the transmission latency is small, but the data is the status that is generated a long time ago. It's not good. Sorry. Yes. I send the data, but the data is not generated as often as possible. It means it's not timely enough. And the other one is I generate as much as I can. This can achieve a good throughput because we utilize every opportunity in the network to deliver data. But this may also not good because, for example, if you send data too often, your data will suffer from a long queuing delay here. And when it's arrived, the destination is also not fresh. Okay, so this is why the age of information concept comes. So the age of information is defined at the time that elapsed since the generation of the packet that was mostly delivered to the destination. At the beginning, it's a bit abstract. You might read it again. So it's the time elapsed since the generation of the packet that was most recently delivered to the destination. So this is a concept coined by Professor Roy Ye's group in 2011. At the early stage, it's not that hard, but recently with more and more IoT application come out, this attract more and more attention. And this, you will see that this AOI captures the freshness of the information from the perspective of the destination. I will use a figure later to explain how to understand this, okay? So in contrast, the packet delay only measures the time interval between the generation of a packet and its delivery. So we will see that this packet delay or the inter-deliver internal is inter-deliver interval is part of the AOI. It's determined by not only delay, packet transmission delay, but also the packet inter-deliver interval. Okay. So let's have a quick example of how AOI evolved during the time. For example, we consider a source is a pair-to-pair system, a source to a destination, and the AOI is measured here actually. So the source may have random generation. So for example, we start with the age of 1 here. Then in the slot 1, G1 means I have 1 packet generated here. Then I use the slot to transmit, use 1 slot to transmit to the destination. And since I assume slotted transmission, and each packet, each update will take 1 slot. And you will see that actually the age goes to 2, and during the slot is keeping 2, and then at the end of the slot, since this generation of packet is received by the destination is going down to 1. And then this is a deliver, means the first deliver of the first packet. So from generation to the delivery only takes, we are lucky. We send is successful, then the OI go down to 1. And then in this duration, there is no, I keep to 1. And then, though I have a generation here, but since it cannot be delivered to the destination, so the age go up, okay? Go up 1 by 1 slot. And then you see that I did not have a chance to deliver it until here. And then the age goes 1 by 1 until here. And then I down to here, okay? Oh, sorry, this is down to here because I try to deliver this. And it's G2, let me see, G2. It's down to here. Oh, sorry. This G2 is lost. Means I try to send G2, and it's get lost. And keep trying until the third one come, third generation come. Because from the status update perspective, once I have new status, I need to always deliver the new update. So I drop this one, I try to deliver this one. I'm lucky I use two slots to get this one delivered here. And then my AOI dropped to 2 because not drop to 0, because it dropped to 2. Why is 2? Because my current data is actually generated 2 time slots ago. Okay, you see that it's basically monitor how fresh the data I receive now. This will keep going because there's no generation until here. There is a generation G4, but G4 was not delivered, so I keep going up. And I have another G5, and then I deliver it. I'm lucky I use 1 slot, and then it's successful. And then the OI drop to 1 because the current packet I received that is generated 1 time slot ago. Okay, so you can see that the AOI time slot T is basically T minus UT. UT is the T time slot, the packet, the fresh packet, the latest packet that I received, the time then the packet generated the transmitter. Okay, it's T minus UT. So basically, there you have to calculate the average AOI. There are a significant amount of work to calculate the average AOI. You will see that we need to calculate the area of this one because it's repeated actually. Although their area is not different, but you see the pattern is repeated. So you get this one sum, and then you average over time, and then you get your average AOI. So we have 2 papers on this. I do not want to go to the details. If you're interested, you can go and read the paper, okay? And here I give you an example to show you what is the difference between AOI and the delay and the inter-deliver time, okay? So consider source to destination network. So we use, this is how queuing people model the channel. They use queue. They use a queue to model the channel. And I assume M1 channel means this is a queuing model, means the generation follows exponential distribution, and the service time follow the exponential distribution, and only have 1 server. So we will calculate the AOI of this system. Okay, so we assume that the exponential of the generation of the packet is follow up parameter lambda. So we will see that whether lambda is large is good or lambda is small is good. Okay, so first one we consider lambda is very small. Lambda equal to 0.1 means I rarely generate a packet, and then your delay is small because actually there is almost empty buffer. Once a generation comes, it gets served instantaneously. We do not need to wait here. But in this case, your inter-deliver time is long because you generate packet not frequently, and your average AOI is actually the sum of them is 01.00. The other one is I generate the packet as soon as I can, almost one packet, one per slot. And in this case, the inter-delivery time is small because the queue is a lot of packets are waiting here to be delivered. Once a packet delivered, the other one will be served. Okay, and in this case, your delay is large. Why? Because the packet need to queue in here for a long time before it gets served. Your average LI is also large. So in this case, you see that when we send lambda equal a medium value, and in this case, the delay is not that large, the inter-delivery time is not that large. And you see a big gap between these two cases and the one with optimized cases. So actually, you compared to a throughput, you see this one. Compare case 1 and case 2. Consider slotted system. In these two duration, you both we use this green one to arrows to denote a packet successfully delivered within the slot. You see that these two cases both deliver 3 packets during this duration. Means your throughput are the same. Okay. But when you calculate the AOI is not the same. The AOI of this one will be much larger than this one. Because if it's easy to understand, because if you want your AOI to be small, you want your packet to come evenly and regularly. Do not come in bursts. If come in bursts, it doesn't make sense because I already know the fresh status. Give me another one, that does not change much. Okay. So this basically is the difference between AOI and conventional metric. You see that they are different. So early works basically focus on the analysis of average AOI. As I mentioned, they're resulting to different queuing theory. For example, first come, first serve, last come, first serve, this lot of things. And this is basically people from networking theory working this. And they consider different topology like point-to-point system, multi-source system, multi-server, multi-hop system already been done. And there are also some new queuing models that was not considered before. For example, they consider M1, something like 2 star, something like this. So this means they allow packet replacement or packet management. For example, if previously, actually, when you consider queuing model, when packet come in, you either can choose first come, first serve, or last come, first serve, but you do not drop packet. But from the perspective of status update, keeping old or stale packet is not meaningful. So we basically can, when we keep only one status update packet here. If a new one come, I just replace this one with the newly come one. So if you are interested with this kind of thing, you may read a book, a short book for which focus on this type of work. Okay. Now we consider the information freshness of why scheduling. So why we consider scheduling? Scheduling is one of the most fundamental problem. I would say fundamental problem. Okay. In wireless networks due to the shared medium, because this is a key feature of wireless communication. There are already a lot of work can be done this or analyzing, designing this throughput optimal or delay optimal multi-user scheduling problem. But as I shared before, I showed before, maybe it's not optimal, no longer optimal when you consider information freshness, when you consider AOI as a performance metric. So here comes a question is how I can schedule the update of multiple users to minimize the expected or weighted sum of AOI of the whole system in the long term. This is actually what we want to answer when we consider AOI-oriented multi-user scheduling. So before I go forward, it's good to clarify that there are two kind of status update arrival models. So basically one is called generator view. Generator view means if I'm scheduled to transmit, I will always generate latest status for my system. For example, For example, if a sensor in this smart parking scenario is put in this smart parking slot, and when the sensor is scheduled to transmit to an AP, it will after it receives the invitation to transmit, it will generate a new status update. Because I want to transmit the latest status update of the system. So we call this one generate view. The other way we may call it random or stochastic arrival. In this case, I only transmit my my generation of the status is actually based on the random process. Means, for example, it's event triggered process. For example, there is a sensor on this on this light, a traffic light detect how many traffic, what is the exact time of the car then turn into this lane. So basically it's a random arrival because I don't know when will be the next car. It's not up to me. It's an event triggered process. So we call this one random arrival. So this area has been led by Professor Modigliano from I think many of you know him from MIT. His group done some early work here. I share you some early work for you to understand what is going there, and then I briefly introduce what we have done, because basically this MIT group is networking theory group, so they did not consider physical layer technologies. So I basically use we basically apply advanced physical layer technology to further improve the performance. So for example, they normally consider is one user per slot, means I schedule user and only have one channel, and I need to ensure there's no collision. I only schedule one user per slot, okay? And they consider that there is a downlink system with M clients, and the time is slotted. They consider frame-based scheduling, but for easy understanding, you can consider slot-based scheduling. Means in each frame there are only t equal to 1 slot. In this case, frame is equivalent to slot-based scheduling. So at the beginning of each slot of frame, base station will the base station is downlink. Okay, it's downlink. The base station will generate one packet per client because it's downlink. It means the base station have some status collected from the internet. It need to inform different clients. So since we consider T here means we only be able to serve one of M client per slot, and we assume that different clients may have different error probability, PI, P1, P2, and PM. So means if I schedule a user, their error probability, their error probability is different. Okay, so this is basically show you how the edge evolve. I already explained this. I skip this. So they consider non-anticipative scheduling policy. And policy, that means policy do not use future knowledge. It's only use what I have to select clients. This set is denoted by pi. So pi, small pi means any arbitrary possible policy in this pi set. So in a slot, k pi, k is frame, k is the frame. And n is the slot. Since they consider frame based, if we consider slot based, there is only a slot k, because frame equal to slot in that case. And we consider the case frame, how we the decision is to be either idle or select a client with an undelivered packet. So this, because there is always generate one packet for each client, means as long as I schedule a client, I will basically do not keep idle. I always need to be active, try to serve one of the clients. So the performance measure is the expected weighted sum LI. Means I want to in the long term, as I shown before, that the LI is there is LI evolution in the long term. I want to minimize the expected weighted sum LI of all users. Means the whole system has a good LI. So if you use this area to calculate, as I mentioned earlier, to calculate the LI, you will have something like this. I do not want to go to the details. So this H is the H, basically the H of the case of the ith user in the cache slot. Okay, HKI is the ith user in the cache slot. It's instantaneous LI. Okay, so and then you can easily formulate this kind of stochastic optimization problem. I want to minimize an expectation of a process, and this is the, you see that this is a weight LI, this is the weighting factor, this is the instantaneous LI of the ith user in the cache time slot at the beginning. Okay, so how to deal with this kind of problem? One way is to you formulate an MDP Markov decision process and solve it by dynamic programming. But this kind of algorithm is normally very computational demanding. So especially when your network has a large number of clients. So we the author want to pursue some low complexity policy, okay? But it's also have good performance. So I think a simple, naive policy is try to schedule the user with the largest age, right? So this is the so-called the greedy policy. I always schedule the user with the largest age, means that user's packet has not been delivered to the destination, has not delivered successful status update to the destination for a long time. So I schedule that user. So for example, in this one is consider each frame has 2 slots, means each frame it can schedule two users. You will see that the greedy policy said this is the instantaneous age of different user. The first time slot is 75422. According to the greedy policy, we basically schedule these two because these two are has larger LI. And then once they are scheduled, since we consider generated view model, the packet generated one time slot ago, and if they're all if their transmission are all successful, then both go to 1. Then since these 3 has not been scheduled, their age has been added by 1, so 533. And then you schedule these 2, right? Because these 2 are the largest one, and you consider there is no error, and then you get this one, right? And all others add, and then you keep going. You see that actually this kind of policy we consider is greedy policies. It's like a round robin, so 1 by 1, 2 by 2, this kind of thing. And the other one is consider symmetric network. Symmetric means the weighting coefficient of different users are the same, means I treat different users equally important. And another one is their error probability is the same. Then it can be proved that this greedy policy is already age optimal. So in this case, actually, we schedule the age, schedule the user that with the maximum age is already optimal. Okay, this it's easy to understand when you think about it, because the potential gain I get, I mean the AOI drop I get is maximum when I schedule the LI, the user with maximum LI, because they suffer from the same error probability. So then how about if there is if the user or the weight of the weighting coefficients of the user are different, and their error probability are different, so it means alpha I not equal to alpha, it can be different. Okay. It can be different. So in this case, maybe is P. Maybe it's not good to always schedule the maximum age. What the insight behind that? Because for example, if you have one user with age 10, but its successful probability is only 0.01, And the other one age with 5, but the successful probability is 0.8. So which one to schedule? So maybe this one, because you have a probability to get something like four on average. You will get some. If I get, for example, if I get this one delivered, then I will have age drop 4 with probability 0.8. And this one I will get a drop of age 9 if I have a successful probability of 0.01. From a risk perspective, you may want to schedule this one. So in this case, not trivial which one to schedule. So the user use VRF optimization to decouple the problem and then finally achieve this kind of weight coefficient, scheduling policy is try to schedule the user that has the value, has the maximum value of pi times alpha I times hk I hk plus 2. So what's the physical meaning of this? I want to schedule some user that has the maximum product of this one. You will see that the error probability, the larger the beta, the weight coefficient larger the beta, and the hk means the instantaneous age, the larger the beta. But it's good to have a product of them to have a schedule decision. But if you have equal alpha and equal p, and you will see that this term is actually equal for different user. It means it's go down to the greedy algorithm. And also in this case, max weight is also edge optimal in the symmetric network. So I hope this will give you some feeling how to schedule in the edge-based network. So since as I mentioned, that is generated view. The other one is random arrival. So random arrival means you have a random process to have a status update packet generated at the base station. So in this case, you need to think about when you schedule the user, you not only think about the age here, but also need to think about how old the packet is here. For example, if you have a packet here is already generated a long time ago, you may do not want to schedule that user. You may want to wait a new update time before schedule that user. So this is another paper from the same group, Professor Modiano's group, consider this case, also downlink. The conclusion is interesting, you will see that. So it's also used max weight policy. It's considered beta is actually the weighting coefficients. P is the transmission successful probability. H is the instantaneous age. C is actually the local age, means how long the packet has been there. So you will see that you need to consider the potential gain you have. When you consider to schedule a user, for example, one user has an age 10 and its local age is 5, okay? And its successful probability is 0.2, for example. Another user is age 12 and its local age means the packet there is 10. So it's also have a probability of 0.2. So in this case, you may want to schedule this user instead of this user because although this age is larger, because in this case, your age drop is 5, but your age drop here is only 2, okay? So you need to consider the gain of you potentially get. So let me go quick here. There is one point we want to argue is our recent paper here accepted by the global com is previously they consider downlink so with random arrival. So if there is uplink with random arrival, what will the case there? So basically when the destination, the access point do scheduling, he do not know the status here, whether there is a new update here or whether the old update has been updated or a new one has been arrived. So this case, I only know the instantaneous AOI of different user of AP, but I do not know their arrival process here. So in this case, it's actually I have a particularly observable system status. So basically, conventional MDP cannot be used to solve this problem. So we use the partially observable Markov decision process to solve the problem. So basically, you need to have a believed state instead of have a real state. So this is what we solved here in this paper. And the other one is previously they consider schedule one user per slot. But on physical layer people, we know that we have several technologies there that support to schedule more than one user per slot. Okay, and this is two work we recently do. One is we apply norma to schedule more than one. But when you apply norma, there is a trade-off here. So if you schedule 2 users per slot, then you potentially have 2 status updates successfully updated. But your error probability of each update is your error probability is larger. So you need to be careful to use hybrid norma and OMA. Sometimes you use norma, sometimes you use OMA. Also we consider downlink because you need to allocate your power to both of them. If you schedule one, you allocate all your power to that client. If you schedule 2, you need to allocate your power, and then the transmission error of each one will go up. Okay, so we formulate that. I do not have time to go to detail. We formulate that as an MDP problem, and we found the optimal policy of switching between norma and OMA, and also we determine the optimal power allocation between them. We also developed the corresponding max weight suboptimal policy. Simulation results said that show that adaptive norma and OMA always have better performance than norma only or OMA only. So another way is till now is most people our work here is published in RCC here this year, is the first work that considered the multi-antenna, because multi-antenna is a well-known technology in physical layer. By using multi-antenna, we basically can also schedule more than one user per slot. But again, there is a trade-off. Schedule more users to transmit at the same time slot, then consider the fixed amount of user. Each user will be able to update more frequently than you only schedule one per slot. But the more you schedule, the higher the error probability that each scheduled user will have, because this is, you have a fixed amount of freedom, degree of freedom. If you use more to do this multiplexing to cancel the interference, you will have less to enhance the SNR of each scheduled user. So then the decision here is which group of user you need to schedule. So we formulate this as MDP, and we also develop a max weight, and we show that schedule the dynamic amount of users is always better than schedule a fixed amount of users. Okay. Here is a recent book. If you want to know more about the scheduling stuff, this is a recent book published in this year, talk about the AOI and the scheduling issues. So let's go quick for the remaining 2 parts. Is we consider another format of scheduling or this access is called random access. Channel access is random. Why random access? Because IoT is going to be massive. Ericsson forecast there will be 28 billion IoT devices by next year. So in this case, central scheduling overhead is too much. And it's good to have decentralized scheduling, means random access. But how we going to schedule the status update for massive IoT device to achieve a low network AOI is another problem we need to address. So this is a generic model that you have a lot of IoT device, they use a common channel. We assume there only one channel, and they want to perform Aloha-like random access to the AP. And we consider the clearance channel means if there is 2 users transmit at the same time, there is a clearance content, and none of them will be received correctly. But we are extending the work to the MPR capability, means multi-packet reception. So, but in this work, we consider that clearance channel. So Professor Roy has already done an early work in 2017. They consider a random access problem. They consider slotted aloha, and the active probability of each IoT device is P prime. It's independent of instantaneous edge. It's basically they do not consider whether I need to change my access probability based on my instantaneous edge. Okay, so they consider generated view model, and Q is basically the successful status update probability. How to calculate Q? Q is basically is 1 minus P n minus 1 power n, because if I want to be successful, I need all other users to be silent, not transmitting, not active. Okay, and then I can easily calculate average AOI by clearance channel. Is something like this. Okay, this is a benchmark for us. So that did not consider the edge dependent random access. I call it edge dependent. So what we do is we recently published a paper on Infocom AOI workshop this year, and we talk about edge dependent random access. So what is the intuition after that? Because we think that the device with relatively smaller AOI should access the channel with a lower probability, such that other devices with larger AOI can achieve a higher successful probability to update their status by encountering less clearance. So if your AOI is small, try to be generous, give the opportunity to others. So I need to observe my AOI. If my AOI is large, I use higher access probability. If my AOI is small, so I need to use a lower channel access probability. So this is what we call edge-dependent random access. So for simplicity, we first consider threshold-based ADRA. If the instantaneous AOI is no less than threshold delta, the IoT device will become active with a fixed probability P. So if otherwise, the IoT device will be stay inactive with probability 1. Okay, sorry for the delay. I think when Chen make announcements, I will try to finish within 10 minutes. Okay. So this is what we propose: threshold-based ADRA. So sorry. So I need to want to say that there is some difficulty in analyzing the AOI of ADRA, because in the AII edge independent, the successful update probability Q of one device is actually independent of the instantaneous AOI of all devices, because they do not consider the AOI before they access the channel. So there is no dependence between AOI and the channel of success, the transmission success probability. But in ADRA, the actual probability of each device is dependent on its instantaneous edge. In that case, the transmission error probability will be dependent on the instantaneous edge of all devices. So this will, how to do this, you can use multi-dimensional Markov chain to model it, but it's very complicated, okay? So we have an approximation on that. Due to time limitation, I do not want to go to the detail. Basically, you get the idea. The idea is we do the approximation, and then we finally get expression for the AOI. It's approximate one, but not exact one. And also in this paper, we show that our performance is better than the edge independent. It's easy to understand because we use more information. It does not make sense if our performance is even worse, right? So it's good to mention that a recent paper did more concrete analysis than what we do. They also have the same model as what we have. We propose the protocol almost at the same time, both published in the same conference, but their analysis is much more solid than us. They consider the exact analysis instead of the approximation, and they also get a lot of good results here. Okay, so how the performance involved, and the network size goes. Network size, the number of users. So if you're interested, you can go to read the paper. So this is the basically the last part is what we've done for we use USRP to develop a prototype, SDR prototype to do this, to verify our LOI oriented design. So this is some information here. I will share the slides later, so I do not want to consume more time here. So, but it's good to do to mention that to achieve this slotted aloha in paper is easy, but in practice it's not that easy, because you need to make sure all the users have been synchronized and their time slot have the same alignment of the time slot, means they have the same local time. So to do that, we need to have a time synchronization scheme over the air. So we basically implement use beacon, means the AP often broadcast the beacon, and different users need to receive the beacon, decode the time, and then adjust its time according to the time clock of the base station. So that's what we do. And we also found that if the experimental results match well with our analytical results, and also, but if we also found that assume coherent channel is very ideal in practice, because if we found that by experiment in real case, even you have a coherent, you may be able to, with a certain probability, that you can still decode both or one of the information. So this is another work we're trying to extend, is try to consider the multi-packet reception capability, and how will this affect the age of information. So basically, this is all what I want to share here. Thanks for your attention. Any comments or questions,